In this lecture, we will discuss the factors that can affect the acidity of a molecule. So let us say the first an acid reaction. What we have a acid Ha. It can dissociate and it can give you A minus and H plus. So if I have a acid, typical acid Ha, it can dissociate and it can give you H plus plus A minus. Now A minus has a tendency to combine with H plus and go back, that is giving Ha. So A minus also has a tendency to combine. In that case reaction will come in the back direction. Ha is called acid, that is it is giving H plus, but if you see A minus, this is taking H plus and forming Ha. So A minus is acting as a base because anything that absorbs H plus is a base. So A minus is a base and corresponding acid is Ha. So we call A minus as a conjugate base. If I see the reaction stability, if A minus is stable, I can say reaction will go mainly into the right direction. And if A minus is less stable, then reaction will go into the left direction. That is A minus will combine with H plus and it will give you Ha. So now I can say if A minus is stable, reaction will go into the right direction. And if A minus is unstable, I can say reaction will go into the left direction. Now if reaction goes into the right direction, this means I will have more H plus, more A minus. That is acid is stronger. If I have more H plus, because this acid is a stronger acid. So if A minus is stable, reaction will go into the right direction and we will call Ha is a strong acid. And if A minus is unstable, in that case reaction will go into the left, that is I have mainly Ha, not dissociated. I will call Ha is a weak acid. So this means I can decide whether I have a weak acid or a strong acid depending upon a stability of A minus. If A minus is stabilized, I will have a stronger corresponding acid is stronger. If A minus is not stabilized, corresponding acid is weaker. So we can say a stability of negative charge can be used to compare the acidity of different compounds. So if I have conjugate base, that is negative charge, this one, stabilized, I will have a stronger acid. If it is not stabilized, we will have a weaker acid. So a stability of conjugate base can be used. Conjugate base, or I can say negative charge species. Can be used to decide acidity. So let us go to the next. So what are the factors that can affect the acidity? And the first factor is on which atom we have the charge, that is atom. Which atom we have the charge? Let us say compare, I have a butane and I have a propanol. I want to compare which one is a stronger acid. So my question is, which of these two is a stronger acid? Idea is same. In both cases, we will lose H plus. So if I lose in this case H plus, I will have CH2 here and one H plus is lost. I will have a negative charge here on carbon. In this case, if I lose H plus, I will have a negative charge on oxygen. So now my question is, which one of these two acid is a stronger acid? And the same can be posed, like we have to look the stability of these two compound, which of the conjugate base is more stable. So we have to see the first factor, on which atom we have the charge. Now in one case I have charge on oxygen, in another case we have negative charge on carbon. Now oxygen is more electronegative and carbon is less electronegative. So charge on oxygen is more stabilized and charge on carbon is less stabilized. So I can say this conjugate base is more stabilized. Because charge we have on more electronegative atom. Oxygen is more electronegative. So corresponding acid will be more acidic. So propanol is more acidic than butane. So this is more acidic. Let us discuss more about atom. If I am going into the row in the periodic table, we have to look the electronegativity. So if you see the previous case, in one case I have negative charge on carbon, in one case I have negative charge on oxygen. So the previous case, if you see, you have one case negative charge on carbon, in one case we have negative charge on oxygen. So now if I am going into the same row, I have to look the electronegativity of atom. So in the same row we look the electronegativity, in the same row we look the electronegativity, and everybody knows carbon is less electronegative, nitrogen is more, oxygen is even more, and fluorine is the most electronegative. So if you go into the row in this direction, electronegativity increases. So I can say if I have CH4, I have NH3, I have H2O, and I have HF. If I make corresponding conjugate base, I will have CH3 minus. In this case, I will have NH2 minus. In this case, I will have OH minus. In this case, we have F minus. Now, which is most stable conjugate base? That is, F minus is most stable because we have atoms, carbon, nitrogen, oxygen, fluorine. They belongs to the same row, and they belongs to the same row. This means I have to look the electronegativity of atoms. So fluorine is the most electronegative, so this is most stable. So stability goes in this direction, so fluorine is most stable. So corresponding acid will be most acidic. So HF will be most acidic. So that acidity will go in this direction. So this is the increasing acidity order. Now let us say the same thing. We have said this compound is more acidic. Now in the same column we look the size. So let us compare the acidity of these two compounds. So my question is, I have H2O and I have H2S. My question is, which of these two is more acidic? So I am interested in more acidic compound. So once again we will follow the same steps. So let us first find conjugate base. So in this case, if I lose H plus, I will have OH minus. And in this case, if we lose H plus, we will have SH minus. So in one case negative charge on oxygen atom, in another case negative charge on sulfur atom. Now if you see, oxygen and sulfur both belongs to the same group. If you are going along the group, we does not look the electronegativity, we look the increasing size. More the bigger size, more the stabilization of charge. So in one case negative charge on oxygen, in another case negative charge on sulfur. Oxygen is a small atom and sulfur is a big atom. So negative charge can be stabilized on sulfur more because the size is big, and this smaller size cannot basically adjust the negative charge. So in this case, sulfur negative charge on sulfur is more stabilized because size is big. So we can say SH minus is more stable. So corresponding acid is, so this is more stable. So corresponding acid is basically more acidic. So we said in the last slide, if you have to compare acidity, first thing you have to look the atom. If you have atom in the same period, that is in the same row, you have to look the electronegativity of atom. And if you are in the same group, that is if you are in the same group, in that case you have to look the size. Like the previous case, you see, if you have fluorine, chlorine, bromine, iodine, you have to see the size. If you have oxygen, sulfur, same group, you have to see the size. And so in this case I can say H2S is more acidic because SH minus is more stable. Now let us do some exercise. We have to find which proton is more acidic. So I have in this case two proton, one proton here, another proton I have here, and we have to decide which proton is more acidic. So what will be the idea? Let us say make the negative charge from here and make the negative charge from here and see the stability. So I have in this case, so if I lose H plus from here, I will have a negative charge on nitrogen, and if I lose this H plus from here, I will have negative charge on oxygen. So now we have one is charge on nitrogen and we have one charge on oxygen. Which is more stable? So we have to see whether nitrogen and oxygen lies in the periodic table. So we have boron, carbon, nitrogen, oxygen, fluorine. So they lie in the same period. So then in the same period we have to look the electronegativity. Oxygen is more electronegative than nitrogen. So this hydrogen is more acidic. So this oxygen is more electronegative. So corresponding conjugate is base is more stable. So hydrogen attached to oxygen is more acidic. Now let us say we have in this case, we have to again find which proton is more acidic. One hydrogen attached to oxygen, another attached to the carbon. So let us make the negative charge. In one case negative charge will come on oxygen, another case negative charge will come on carbon. Now we have same period. Oxygen is more electronegative, so this oxygen will more stabilize. So this hydrogen attached to oxygen is more acidic. So I can say this hydrogen is more acidic. Now once again we have to find which hydrogen is more acidic. In one case we have on nitrogen, another case we have on carbon. So if I make the negative charge, in this case I will have negative charge on nitrogen. So let us make this one. So in one case I will have negative charge on nitrogen, in another case I will have negative charge on carbon. So nitrogen and carbon both belongs to the same period, BCNOF. So nitrogen is more electronegative than carbon. So this hydrogen, that hydrogen in blue, is more acidic. Now let us say here we have, if I try to make negative charge, in one case I will have negative charge on sulfur, another case I will have negative charge on oxygen. Now they belong to the same group because oxygen, sulfur, cellurium, tellurium. So in group BC the size, sulfur is bigger in size, so this is more stabilized. So this means hydrogen attached to the sulfur is more acidic. So this hydrogen is more acidic. Now let us say this one again. We have the same idea. So one negative charge on nitrogen, another negative charge we have on oxygen, and nitrogen oxygen lies in the same period. We have to see the electronegativity. Oxygen is more electronegative, so this is more stabilized. So this means hydrogen attached to oxygen is more acidic. Now the second factor we have, that is resonance. So we discuss the first factor to decide acidity is the charge on which atom we have. Now if I have a atom that belongs to the same period, we have to look the electronegativity, and if my atom belongs to the same group, we have to look the size. Now the second factor, important factor we have, that is resonance. Now let us say we have these two molecules. One is ethanol, another is acetic acid. If we try to compare the acidity of these two molecules, in one case I will have, if we make the conjugate base, in this case I will have this conjugate base, and in this case I will have this conjugate base. Now you see, in both cases I have negative charge on the same atom, that is oxygen here. So factor 1, that is the atom on the charge on which atom we have, cannot be used to decide which is more acidic. So I can say factor 1, that is charge on atom, cannot be used to compare acidity. So now we'll go to the second factor, that is resonance. So resonance can help to decide the stability of corresponding conjugate base. So let us say in the same case we can make, in this case, corresponding conjugate base is this, and in this case we have conjugate base is this. Now if you have some idea of resonance for this molecule, we can write one resonating structure. This goes here and this goes here. So I have another resonating structure. This means this charge is delocalized. So this charge on this oxygen as well as on this oxygen. So this molecule, so corresponding conjugate base is more stable because charge is delocalized, but in this case charge is localized, so this is less stable. And in this case we have charge that is basically delocalized. So if charge is delocalized, I can say this corresponding conjugate base is more stable. So this negative charged spaces, this one and this one, both are basically resonating structures. These are more stable. So corresponding acid is basically a stronger acid. Now let us do the some exercise. I have two proton. I have a proton here, I have a proton here, and we have to decide which proton is more acidic. Idea is same. We have to make the corresponding conjugate base. That is, if I make n minus here, and in this case I can make a negative charge here. So if I lose this H plus, I will have a lone pair also. I lose H plus here, I will also have a lone pair. That is, one lone pair is already, and I will have one more lone pair, and that's why we have a negative charge. Now in this case this charge is localized, there is no resonance, but in this case there exists a resonance. This can go here and this can go here. So this hydrogen, that is hydrogen in blue, hydrogen attached to this nitrogen, is basically more acidic because charge is delocalized. So in this case charge is delocalized, but in this case charge is localized. So I can say this hydrogen is more acidic. Now let us say I have two hydrogen, one hydrogen here and one hydrogen here. We have to look which is more acidic. Idea is same, we have to make the corresponding conjugate base. I will have negative charge here, and in this case I will have a negative charge here. If I use factor 1, that is charge on atom, cannot be used because in this case charge is also on carbon atom. In this case also we have charge on carbon atom. So factor cannot be used, that is charge on atom cannot be used to decide the acidity. But resonance can be used. We can make a resonating structure, this goes here and this double bond goes here. So I can have another resonating structure of this molecule, something like this. This means this negative charge is basically delocalized, but this negative charge is localized. So this negative charge is more stable. This means hydrogen corresponding to this negative charge is basically more acidic. So this hydrogen, that hydrogen in blue, is more acidic. Now let us say in this case, we have two hydrogen. You can do yourself. Now let us make the corresponding conjugate base. Here we have nitrogen and this side CH3, negative charge. Now this negative charge is basically delocalized by the benzene ring, but this negative charge is not delocalized. So this negative charge is just stabilized. So corresponding H plus is more acidic. So this hydrogen is more acidic. Now this one, let us try to do this one. Again we have to make the corresponding conjugate base. So let us make two different structure. In one case, if I lose this hydrogen, I will have this species, and if I lose this hydrogen, I will have this species. Now if you see this species, this is resonance stabilized. I can go here and this can go here. But in this case, this negative charge is not resonance stabilized because this basically, I cannot write something like this. So this is not resonance stabilized and this is resonance stabilized. That is, charge is delocalized. So I can say this hydrogen, that is hydrogen in red, is basically more acidic. Now here we can say charge is localized. It is not in the part of delocalization. Now let us compare these two. Without drawing, you can say this hydrogen, you can have a resonance here. In this case there is no resonance. So this hydrogen is red, is basically more acidic. If you wish, you can draw two resonating structures or two separate structure and then you decide. Let us say if I lose H plus, that is in red, so I will have this one, and if I lose this one, I will get this species. And let us compare the acidity or conjugate base stability. So in this case this is resonance stabilized, but this is not resonance stabilized. So in this case charge is basically localized, and in this case charge is delocalized. Now in this case again you can say, in one case you have here and in one case you have hydrogen here. So let us make two separate conjugate base. If you lose this H plus, you will have negative charge here, and in this case you have OH. Now in this case, if you lose H plus from here, you will have O minus. Now you see, in this case I have a negative charge on carbon, and in this case I have negative charge on oxygen. So factor 1 is basically used. So I have charge on carbon and I have negative charge on oxygen. Oxygen is more electronegative because we are going in the same period, that is boron, carbon, nitrogen, oxygen, fluorine. So One time we have negative charge on carbon, another time we have negative charge on oxygen. Oxygen is more electronegative because in the same period we look at electronegativity. So this negative charge is more stabilized. So I can say this hydrogen is more acidic. So you see in this case basically resonance is not used. Factor, that is number of on which atom we have charge, is basically used. So let us say in this case once again we can use on which atom we have charge. In this case we have charge on oxygen, in this case we have charge on carbon. So this hydrogen is more acidic. So hydrogen attached to oxygen is more acidic. Now let us say we have this molecule is vitamin C, and which proton is most acidic? We have this proton, this proton, and this proton, this proton. So there are a large number of protons. We have hydrogen here, we have a hydrogen here, we have a hydrogen here, we have hydrogen here. Which hydrogen is more acidic? Now if you see in this case we have a negative charge on oxygen. If I remove H plus from here, a negative charge on oxygen, remove H plus from here, negative charge on oxygen, remove H plus from here, negative charge on oxygen. So in all cases we have negative charge on oxygen. So factor 1 cannot be used to decide the acidity. Now let us go to the factor 2, that is resonance. On this case for this oxygen there is no resonance. Even for this oxygen, basically for this oxygen there is no resonance. I have resonance for this oxygen as well as for this oxygen. So let us decide which resonance is powerful. So I can make this only a small part of the molecule, so we are not making the whole. So I have this one, so I'm making the only a small portion of vitamin C. So let us say in one case I am making negative charge on this oxygen. I have a double bond here and I have a OH group here, and let us say here I have oxygen, and here this side we have, let us say, OH, and this side also we have OH. Now this negative charge is resonance stabilized. This can go here and this can go here and this can even go here. Now if you see, if I have a negative charge on this oxygen, so let us make the corresponding conjugate base. OH. If I make negative charge here, I can have a resonating structure, but this can be stabilized only this side. If you see this resonating structure, there are 3 arrow flow, that is more delocalization, and in this case there are only 2 arrow flow, that is less delocalization. So the hydrogen corresponding to this oxygen is more acidic. So this hydrogen is more acidic. And the idea is simple because this, in this case we have more delocalization. Now let us say we have these two molecules, so we have negative charge on this oxygen, and if I say in this case also we have negative charge on oxygen, so charge on atom cannot be used. So let us say we can make 2 conjugate base. So if I make conjugate base from this oxygen, we will have negative charge, and if I make conjugate from base from this oxygen, I will have negative charge on oxygen. In this case we can write resonating structure, so this goes here, this goes, so this benzene ring. Now in this case we can also write resonating structures, this goes here and this goes here. Important point in this case, if I make resonating a structure, the second time negative charge goes onto the carbon. In this case, negative charge goes onto the oxygen. So even though we can write more resonating a structure for this molecule, all are not so powerful because in this case negative charge goes into the oxygen. Negative charge on oxygen is more stabilized than negative charge on carbon. So I can say this molecule that is more stable because we have negative charge on oxygen. So in this case we can say negative charge goes on carbon, but in this case negative charge goes on oxygen. So negative charge on oxygen is more stable than negative charge on carbon. So corresponding conjugate base is more stable. So this is more stable. So corresponding hydrogen is more acidic. So this hydrogen is basically more acidic. So we discussed two factors, that is charge on atom, which atom we have charge, and we have discussed resonance, how the resonance can stabilize the conjugate base and correspondingly can increase the acidity of molecule. Now the third factor we have, that is induction, that is inductive effect. Let us say we compare the acetic acid and trichloroacetic acid acidity. I have a hydrogen here, this hydrogen is acidic and this hydrogen is acidic. We have to compare which hydrogen is more acidic. So what we will do, we will make the RDI same, we will make the corresponding conjugate base. So in this case I will have conjugate base this, and in this case we have corresponding conjugate base O minus, and we have 3 chlorine. Now see what will happen, chlorine has a tendency to attract electrons, so this bond pair will go this side, this electron will also go this side, so this electron will go this side. So what will happen, this negative charge has a tendency to stabilize by the inductive effect, but this negative charge is not stabilized by inductive effect. So while the resonance stabilization, this resonance stabilization is also here. In this case we have an extra stabilization, that is inductive effect. That is the effect because of more electronegativity of chlorine. Electron cloud on oxygen will get attracted towards chlorine, so it will stabilize more. So this oxygen is more stabilized, so corresponding hydrogen is more acidic. So I can say this hydrogen is more acidic. Now in these cases we have to decide which proton is more acidic. So you see in this case I have hydrogen, I have chlorine here, so it can show some inductive effect. In this case I have 2 chlorine, it can show even more inductive effect. In this case I have 3 chlorine, so it can even show more inductive effect. So this case this is most acidic, and this one is basically least acidic. Now let us say we have these two protons. So this proton, oxygen, hydrogen, oxygen, hydrogen. So which hydrogen is more acidic? Either this one or this one. Now in this case, negative charge on oxygen. In this case also negative charge on oxygen. So factor A term cannot be used. Now you see, in this case fluorine will do inductive effect. So it will try to pull electrons. It will try to pull electron. Now this negative charge, oxygen negative charge, is more close to this fluorine group. So this will be more stabilized and this will be less stabilized, because inductive effect is a distance dependent effect. So this negative charge will be less stabilized because it has basically away from this fluorine group. So inductive effect depends upon distance. And that's why I can say this hydrogen is more acidic. Now let us say in this case I have hydrogen here, I have a hydrogen here. Now this hydrogen negative charge on oxygen, this hydrogen negative charge on oxygen, this CF3 group will try to pull electrons, that is minus I effect. So it will show minus I effect and distance dependent effect. So this negative charge is more stabilized and this negative charge is less stabilized. So this hydrogen is more acidic. Now let us say in this case I have negative charge on this oxygen, negative charge on this oxygen. These two chlorine group will try to pull electrons, that is minus I effect, and this is very close to this group because in this group I have a CH2 in the middle. So it will stabilize this hydrogen more because inductive effect is a distance dependent effect. So this hydrogen is more acidic. So let us say I have two acids. We have to decide which hydrogen is more acidic. Either this hydrogen is more acidic or this hydrogen is more acidic. Once again, in this case I have only one chlorine, in this case I have two chlorine. So this will show minus I effect more compared to this one. So this hydrogen is basically more acidic. Now decide yourself, I have a hydrogen here and hydrogen here. Which hydrogen is more acidic? And you have to remember that inductive effect is a distance dependent effect. So this Br can show minus I effect, this Br can also show minus I effect, but the point is this Br is away from this carbon and this Br is basically just besides this carbon. So this will show minus I effect more. So this hydrogen is more acidic. So I can say this hydrogen is more acidic. Now the fourth factor. So we discuss what are the factors we discussed. First we have to look which charge on which atom we have, and then we said what is the resonance, and the third factor that we are going to discuss is orbital. So charge resides in which orbital. So let us compare the acidity of these two hydrogen. So if I make corresponding conjugate base, what we will have negative charge here, and in one case I will have negative charge here. Atom cannot be used because you see in both cases we have negative charge on carbon atom. Resonance idea cannot be used because we cannot have resonance for this as well as for this. Now we have to look orbitals. If you see what is the negative charge, in which orbital this resides and in which orbital this resides. So if I ask you, so let us say this question, if I have what is the hybridization of this carbon, so what you will say. So this has two groups attached, so hybridization basically 1 to 3 groups, or let us say this carbon 1 group, 2 group, 3 groups, so hybridization is sp2. For this carbon, once again this is 1, this is 2, and this negative charge with one lone pair of electron, so hybridization is sp2. And what is the hybridization of this carbon? This has two groups attached, one group, two groups, so hybridization of this carbon is basically sp. So this is sp2 and this is sp. This means in one case negative charge lies on sp2 orbital, in another case sp orbital, so negative charge lies on sp orbital. So we have to look which charge is more stable, that is negative charge in sp orbital is more stable or negative charge in sp2 orbital is more stable. To answer this question, let us say if I have sp orbital smaller in size, and sp3 orbital that is bigger in size. So if I have a center, so sp3 orbital is away from the center, so I can say sp is more close to nucleus. And this can also be verified. What is the s character in sp orbital? What is the percentage s character? So if I say total is 100, so s is, because we have two s and p characters, so this is 100, so s character is 50% and p character is also 50%. So that is more close to nucleus. Now sp2, what is the percentage s character? Now in this case percentage s character is only, so we have 3, so only 33%, so 100 by 3, that is 33.3%. So we have 3, 1s and 2p, and all comes out to be 100, so this is 100 divided by 3, so 33%. So sp has more s character, that is more close to nucleus, and sp2 has less s character and less close to nucleus. So I can say sp2 is less close to nucleus, and sp3 is even less close to nucleus. So negative charge very close to nucleus is more stable, that is negative charge in sp orbital is more stable. So we can say negative charge on sp orbital is more stable. Using this idea, we can say in this case negative charge on sp orbital is more stable, so this hydrogen is basically more acidic. So this hydrogen is more acidic. Now let us say we have three compounds. We have to compare which hydrogen is more acidic. So in this case we have CH3, CH3. So if I make negative charge, I will have CH3, CH2 minus, conjugate base. In this case I will have CH2, double bond CH minus. In this case I will have CH, triple bond C minus. Now you see in this case negative charge, if you compare the hybridization of this is sp3 hybridized and this is sp2 hybridized, and this one is basically sp hybridized. So we have already said negative charge on sp hybridization is more stable than negative charge on sp3 hybridization. So acidity goes in this order. So this is most acidic and this is least acidic. Now let us say in this case, if you see this is sp3 hybridized and this is sp2 hybridized, so negative charge we will have in sp2 and in this case negative charge we will have in sp3. So this hydrogen is more acidic. Why? The reason is same. Negative charge we have in sp2 orbital and in this case we have negative charge on sp3 orbitals. Now let us say we have two hydrogen. In one case we have hydrogen here, that is amine group, so this hydrogen, and in this case imine. Which hydrogen is most acidic? Once again we have to make conjugate base minus. In this case I will have R N minus. Now we can use atom because in both cases we have negative charge on nitrogen. We cannot use resonance because there is no resonance. Induction is also not important in this case. So now we have only one option, that is orbital. In this case, what is the hybridization of this negative charge? That is this is sp hybridized and this is, we have a lone pair also here. So we have to compare. So this is sp2 orbital. So let us write this lone pair. So you see how many groups we have? One group, two group, three groups. So this is basically sp2 and in this case we have four groups. So this is sp3. So in this case negative charge we have in sp3, and in this case we have negative charge in sp2 orbitals. So this hydrogen is basically more stable or more acidic. Now ranking the factors, so we discussed four factors: atom, resonance, induction and orbital, and the ranking of the factor is same as we discussed. That is, we have to see first atom, and then we have to see resonance, then we have to see induction, and then we have to see orbital. That is, if I have a conflict between resonance and atom, we have to see the atom first. If I have a conflict between resonance and induction, we have to give priority to the resonance. If I have conflict between orbital and induction, we have to give priority of induction. So this is the priority order. So I have to give first priority to the atom and the last priority to the orbital. Now let us say I have some example. I have this molecule, in this case negative charge on oxygen, in this case I will have negative charge on carbon. Negative charge on oxygen and one case carbon. So I have to look these factors. So first factor is atom. So atom is enough to decide, because in one case I have negative charge on oxygen. Oxygen is more electronegative than carbon. So hydrogen attached to ethanol is more acidic. So this hydrogen attached to oxygen is more acidic. So let us say once again we have this hydrogen and this hydrogen. In one case I have negative charge on this oxygen, in another case I have negative charge on this oxygen. In both cases we have negative charge on oxygen, so atom cannot be used. Now next factor we have resonance. In this case I have resonance, so let us say make this molecule with negative charge. So I have CCl3 and I have O minus. In this case I have resonance. In this case I does not have a resonance. You can say that there is inductive effect due to the CCl3. But now inductive and resonance is more priority order. So we have discussed ranking. So resonance is more important. So this means this hydrogen is more acidic. So hydrogen attached here is more acidic. Now let us say in this case I have this hydrogen and this hydrogen. So let us say if I make corresponding conjugate base, in one case I have negative charge on oxygen, in another case negative charge we will have, that will come on carbon. Negative charge on oxygen is more stable, so this hydrogen is basically more acidic. Now let us say in this case, once again we can make the corresponding conjugate base. So if I remove this hydrogen, I will have negative charge here, and if I remove this hydrogen, I will have negative charge here. Now in this case we have resonance, in this case also we have resonance, but the important point we have in this case, we have two-sided resonance. So this negative charge can be resonance stabilized this side, and this can be also resonance stabilized this side, because we have two resonating structures possible. So in this case we have more delocalization, in this case we have less delocalization. So this hydrogen is more acidic. So I can say in this case we have more delocalization. So we have resonance both sides. In this case we have resonance only one side. Now let us say this molecule. So we have hydrogen here, we have hydrogen here. So now we have negative charge in this case on nitrogen, we have negative charge in oxygen. So atom factor 1 can be used to decide. So which hydrogen is more acidic? This hydrogen is more acidic because we will have negative charge on oxygen. Oxygen. So corresponding hydrogen is more acidic. In this case we have negative charge on nitrogen. So if I are in the same period, we can look the electronegativity, and oxygen is more electronegative than nitrogen. So I will have this hydrogen is more stable. This hydrogen is more acidic. Now in this case again we have, so let us say if I make corresponding conjugate base, if I lose this hydrogen, I will have a negative charge here, and let us say if I lose this hydrogen, so I will have a negative charge here. Now you see in this case both negative charge, we have negative charge on carbon, we have negative charge on carbon. So factor A term cannot be used. Now in this case we have resonance, this can go here and this can go here. But in this case there is no resonance stabilization. So this hydrogen corresponding to this negative charge, that is this hydrogen, is basically more stable. And now which factor more stable, or I can say hydrogen is more acidic. So which factor is used? So factor resonance is used in this case. Now let us say we have two hydrogen in this case. Now this hydrogen as well as this hydrogen. So in one case let us try to make corresponding conjugate base, or you can directly define. In this case you will have, if you lose this H plus, negative charge will come on carbon, and in this case negative charge will come on nitrogen. So atom factor is sufficient because negative charge on nitrogen is more stabilized than negative charge on carbon. So I can say hydrogen attached to nitrogen is more acidic. Hydrogen attached to nitrogen is more acidic. And reason is same, nitrogen is more electronegative than carbon. So here we have negative charge on carbon, and here we have negative charge on nitrogen, and negative charge on nitrogen is more stabilized. Now let us say in this case, once again we have negative charge on sulfur in this case, and in this case we have negative charge on oxygen. If we are going into the group oxygen, sulfur, cellurium, tellurium, so we have to see the size. So sulfur is bigger in size, it will stabilize more. So this hydrogen is more stable or more acidic. So if you are going into the group, we have to look the size. If you are going into the period, we have to look the electronegativity. Now let us say in this case we have negative charge on nitrogen, and in this case we have negative charge on carbon. Now in this case you have negative charge on nitrogen, in this case you have negative charge on hydrogen, sorry, negative charge on carbon. So let us say we will have, in this case if I make, so triple bond we have, and then we have carbon, then we have nitrogen, so this is CH2, and negative charge in one case we have on nitrogen, in another case we have on carbon. Now if you see negative charge on nitrogen because atom, and this on carbon, so nitrogen looks like it is more stable than carbon. Now this is exception, that is if I say this negative charge is more stable, or this hydrogen is more acidic corresponding to this hydrogen, it looked like that hydrogen attached to nitrogen should be more acidic because negative charge on nitrogen is more stable than negative charge on carbon. So this hydrogen should be more acidic. But this is exception, and we'll discuss in the last also. This hydrogen is basically more acidic. And this is the exception. We'll discuss in the last. So this is the exception. Now let us say in this case we have negative charge on oxygen. Here we have negative charge on oxygen. In this case we have resonance. In this case also we have resonance. So let us say and if I make this one, so in both cases we have resonance. But after resonance, in this case negative charge comes onto the carbon. In this case negative charge comes onto the oxygen. So delocalization in this case is more stable because negative charge, we have always negative charge on oxygen. In this case we have negative charge on oxygen and sometime on carbon. Negative charge on carbon is less stabilized. So this is more stabilized. So this hydrogen is more acidic. Now let us say in this case, once again in this case we have negative charge on oxygen and in this case negative charge on nitrogen. So this is more stable because this is more electronegative. So factor atom can be used in this case and corresponding hydrogen is more acidic. Now let us discuss about exception. So we said acetylene and ammonia. If you see acetylene, if you make the corresponding conjugate base, I will have NH2 minus here. So it looks like negative charge on nitrogen, that is more electronegative atom. So by rule whatever we have discussed, negative charge on nitrogen is more stable than carbon. So this is more acidic and this is less acidic. So one can expect, so expected is this is less acidic and this one is more acidic. But the observation is different. This becomes more acidic and this becomes less acidic. And this can be basically explained on the basis of orbital. In this case you have negative charge in sp orbital, that is the, if you see hybridization of this has two groups, so this is sp. Now if you see hybridization of nitrogen, this is sp3. So negative charge we have in sp3 orbital. So negative charge in sp, that is more close to nucleus. So in this case basically factor orbital supersede the factor of atom. So in this case factor orbital becomes more important, is more important than atom. Than factor of atom. So you see what we discussed in all this slide, that is we have to look the first acidity of conjugate base if I am interested in acidity of a compound. Now how to look the conjugate base stability? So we discussed there are four factors: atom, resonance, inductive effect and orbital. In case of atom we said if I have a atom in the same period we have to look the electronegativity. If I have two atoms in the same group we have to look the size. And in the last we said there is one exception, that is ammonia and acetylene. It looks like ammonia should be more acidic, but the fact is acetylene is more acidic than ammonia. That is factor of orbital plays important role in this case.